Hi, this is Dr. O'Connor. Welcome to Pathways to Chemistry. Here we're given a reaction between hydrogen gas and iodine gas to produce hydrogen iodide. And we're also shown the observed rate law, and this is right here. By observed, remember that is the rate law that's determined from experiment. And we're given the proposed mechanism, and we're asked, is this mechanism consistent with the observed rate law? Well, a few criteria that need to be met. And first off, we have to look at the elementary steps here and make sure they're reasonable, and they look reasonable to me. We have two fast equilibrium steps, a slow step. Here we have a unimolecular elementary step, and here two bimolecular elementary steps. So they look reasonable to me. Second, we have to make sure that the elementary steps sum to our overall equation. So let's go ahead and add these. Let's see, this, and this cancel, and of course these cancel here. And let's go ahead and add these and see what we get. So we get the iodine gas plus hydrogen to yield 2 hydrogen iodides. So yes, that's the elementary steps do add up to the overall equation. So we're good there. Now, the final criteria, what we need to do is make sure that our rate law that is determined from the mechanism is consistent with the experimental rate law here. So as we know, we always write a rate law from the slow step. So that would be our third step. So the rate would be equal to K3, and that'd be concentration of this species times the concentration of this species. Well, we have a bit of a problem here because we know that the rate law must be in terms of reactants and not in terms of intermediates. These are intermediates. How do we know? Well, an intermediate is generated in one step of a mechanism and consumed in another step. So we can't have our rate law in terms of intermediates. Let's work with the first step, and in the first step here is a fast equilibrium step. So we know at equilibrium the rate of the forward is equal to the rate of the reverse reaction. So let's go ahead and write out the rates for those. So we have K, and that's going to be K1, and let's see, that'll be iodine, and then let's write the reverse rate, and that would be this squared. So what we need to do is we need to solve for the intermediate, because again, we want to get this rate law in terms of reactants. So let's do this over here, and what we would have is K1 over K inverse, and this would be times this, and this would all be that'll be the square root of this, okay, and that would equal the intermediate concentration here. So we have that done. Now let's do the same for the second elementary step, the second fast equilibrium elementary step. So we can write the forward rate as K2. We have hydrogen gas, and then we have this gaseous iodine atom, and that's equal to K minus 2. And we have this species here. Let's go ahead and solve for the intermediate. And what we have here is, let's see, K2, K minus 2, and that'd be H2 and the iodine atom. Okay, so I'm going to go to the rate law that I wrote from my slow step, and I'm going to start substituting. So I think first I'll go ahead and substitute this in for this intermediate here. So that would give us rate is equal to K3. Let's go ahead and combine these K's, or put them together. That's K minus 2. I'll show you what we do with them at the end. So we have the K's here, and then we have hydrogen and we have this. And don't forget this. Remember, all of this substituted for this, and then we have to bring this down as well. And then I'm going to go ahead and clean this up a bit. So I have my rate is equal to K3, K2, okay, and we have this in terms of hydrogen, which is a reactant, and we have this species here, okay, squared. So now I have to eliminate this. And what I can do then is substitute this in, okay, for this. So let's go ahead and do that. So rate is equal to K3, K2, K minus 2. And I'm just going to go ahead and bring these K's over here. So that'd be K1 over K minus 1 to the 1/2 power. Okay, so let's see. So we have the hydrogen here, so we want to keep that in there. Now, this here, remember what we have here is this species squared. So I'm going to go ahead and put that in like so. And what we have is we have this to the 1/2. Okay, so cleaning this up a bit, we have rate is equal to, now these K's, these are all constants, and a constant times a constant divided by a constant divided by another constant is always a constant. So I'm just going to call that constant K, and here we have our hydrogen, and this then is just going to be the iodine. So we can go ahead and compare this to the experimental rate law, which is here. So yes, this mechanism is consistent with the observed rate law. So this is a plausible mechanism. Actually, it's an accepted mechanism.